Okay, so hi you guys again, Algebra 2 scholars. We're going to be going over solving linear systems, which we went over in the 0 chapter, but in particular, this one is with 3 variables. So every time you have another variable, you need another equation. So far, what we've done is solving linear systems in 2 variables, an x and a y. Now we're going to throw in a z. So these problems are more like real life. They're big and they're messy, but they're super fun and satisfying when you get them done. So here's some of the vocabulary. We're going to try to first visualize those solutions because it's actually 3 planes coming together. We're also going to talk about algebraically how to solve it. And then there's one real life problem thrown in at the end. So we'll have linear equations with 3 variables, an x, a y, and a z. A system, remember, means more than one equation. The solution of a system is given in the form of an ordered triple, because if you have 3 planes, they will meet together in one point in space. So that's that. If you look at what these look like, if you have 3 different planes, okay, like this, where each plane is represented by an equation with 3 variables, then you'll have exactly one solution if they look like this, if they intersect in exactly that way. Now, if they intersect in this way, they will intersect all 3 planes together in a line. So that's basically infinitely many solutions. All 3 planes intersect together. And then the ones where there's no solutions have a number of different ways they could be. Like here, even though 2 of them have solutions, all 3 do not. 2 have solutions, no solutions here. They could all be parallel. So we have the same possibilities as we do with 2 equations and 2 unknowns. It just looks a little different. And remember, our solution is going to be an ordered triple x, y, z, where it's a parenthesis, x, comma, y, comma, z, end parenthesis. So basically, it's the same as solving a system. You make one of the variables go away, and you go from there. But with 3 variables, we have to make at least one go away from both. And then you have a system that we have previously solved for, and then you go back and plug it in. It's all very methodical. So here's the steps. Step 1, rewrite the system in 3 variables as a system in 2 variables by using substitution or elimination. That's the first step. Then you solve those 2 for one of the variables. Then you take that variable you solved, plug it back in to one of the originals, and solve for the remaining variable. So it's just a little extra. But when you get a false equation, like for instance, you get 0 equals 1, then you know that this system has no solution. But if you don't obtain a false solution, you get like a 5 equals 5 or 0 equals 0, then you know that it has infinitely many solutions. So the resulting intersection is a line. Here is an example. We're going to do one example and then we'll do one together as a class.
Solve the system given by equation 1, 4x plus 2y plus 3z equals 12. Equation 2, 2x minus 3y plus 5z equals negative 7. And equation 3, 6x minus y plus 4z equals negative 3. Solution. Step 1. Rewrite the system as a linear system in 2 variables. The coefficient of negative 1 in equation 3 makes y a convenient variable to eliminate. Add 2 times equation 3 to equation 1 in order to eliminate y. So 4x plus 2y plus 3z equals 12 plus 12x minus 2y plus 8z equals negative 6. Add the like terms appearing in the same column to get 16x plus 11z equals 6, which you can call the new equation 1. Add negative 3 times equation 3 to equation 2 in order to eliminate y. So 2x minus 3y plus 5z equals negative 7 plus negative 18x plus 3y minus 12z equals 9. Add the like terms appearing in the same column to get negative 16x minus 7z equals 2, which you can call the new equation 2. Another way, in step 1, you could also eliminate x to get two equations in y and z, or you could eliminate z to get two equations in x and y. Step 2, solve the new linear system for both of its variables. Add new equation 1 and new equation 2 in order to eliminate x. So 16x plus 11z equals 6 plus negative 16x minus 7z equals 2. Add the like terms appearing in the same column to get 4z equals 8. Solve for z to get z equals 2. Substitute z equals 2 into equation 1 or 2 to find the value of x. X equals negative 1. Step 3. Substitute x equals negative 1 and z equals 2 into any of the original three equations and solve for y. First, write original equation 3. 6x minus y plus 4z equals negative 3. Substitute negative 1 for x and 2 for z to get 6 times negative 1 minus y plus 4 times 2 equals negative 3. Solve for y equals 5. So the solution is x equals negative 1, y equals 5, and z equals 2, or the ordered triple, negative 1, 5, and 2. You can check this solution in each of the original equations.
I hope that that makes sense. You've got a number of different choices along the way. This is another example where you get no solution.
Solve the system given by equation 1, x plus y plus z equals 2. Equation 2, 5x plus 5y plus 5z equals 3. And equation 3, 4x plus y minus 3z equals negative 6. Solution. Step 1. Rewrite the system as a linear system in two variables. Add negative 5 times equation 1 to equation 2. So, negative 5x minus 5y minus 5z equals negative 10, plus 5x plus 5y plus 5z equals 3. Add like terms appearing in the same column to get 0 equals negative 7. Because you obtain a false equation, the original system has no solution.
So you can see when you get a false one, just like before, no solution. This is another example where you get the same thing equal to itself. You get an identity, and so that's many solutions. I'm going to continue on because I want to do the real life example. These are examples we can do together in class, but this is where I wanted to get to. So let's say we have a real life problem. We have three different unknowns, and we have three different equations. We want to solve it.
An amphitheater charges $75 for each seat in section A, $55 for each seat in section B, and $30 for each lawn seat. There are 3 times as many seats in section B as in section A. The revenue from selling all 23,000 seats is $870,000. How many seats are in each section of the amphitheater? Solution. Step 1. Write a verbal model for the situation. Let X be the number of seats in section A, Y the number of seats in section B, and Z the number of lawn seats. You know that the number of seats in B, Y, equals 3 times the number of seats in A, X. You also know that the number of seats in A plus the number of seats in B plus the number of lawn seats equal the total number of seats, which is 23,000. Lastly, you know the number of seats in A sold at $75 each plus the number of seats in B sold at $55 each, plus the number of lawn seats sold at $30 each, equal the total revenue of $870,000. Step 2. Use the verbal model to write a system of equations. Equation 1 describes that there are 3 times as many seats in section B as in A, or y equals 3x. Equation 2 describes that the total number of seats is 23,000, or x plus y plus z is 23,000. Equation 3 describes the total revenue from the 3 sections, or 75x plus 55y plus 30z equals 870,000. Step 3. Rewrite the system in Step 2 as a linear system in 2 variables by substituting 3x for y in equation 2 and 3. First, write equation 2. X plus y plus z equals 23,000. Substitute 3x for y to get x plus 3x plus z equals 23,000. Simplify to get 4x plus z equals 23,000. You can call that new equation 2. Then write equation 3. 75x plus 55y plus 30z equals 870,000. Substitute 3x for y to get 75x plus 55 times 3x plus 30z equals 870,000. Simplify to get 240x plus 30z equals 870,000. You can call that new equation 3. Step 4. Solve the new linear system for both of its variables. Use elimination. Add negative 30 times new equation 2 to new equation 3. So, negative 120x minus 30z equals negative 690,000 plus 240x plus 30z equals 870,000. Add to get 120x equals 180,000. Solve for x to get x equals 1,500. Substitute into equation 1 to find that y equals 4,500. Substitute into equation 2 to find that z equals 17,000. Study tip. When substituting to find values of other variables, choose original or new equations that are easiest to use. So the solution is x equals 1,500, y equals 4,500, and z equals 17,000. Or the order triple 1,500, 4,500, and 17,000. So there are 1,500 seats in section A, 4,500 seats in section B, and 17,000 lawn seats.
And that's how you solve a problem like this in the real life. Again, there's some examples that we can do together in class, and then it's time to practice what you just learned in exercises on the Big Ideas platform.